Hello? Can you hear me? Yes? So today's morning session is on string cosmology. And there is one simple definition of what are observables at this session. We take our telescopes, we look at the sky, we make observations, that's it, easy. Anshuman, you can start.
I'd like to begin by thanking the organizers for putting together Strings 2025 and also the invitation. I've been asked to review the subject of string cosmology. Let me start with some resources. The annual conference on string phenomenology was around 6 months ago. A lot of the recent developments were discussed there. And also, there have been 2 recent reviews on the subject. They're very good for the standard material and the references. Okay, so now let's look at the plan of the talk. Research in string phenomenology takes place in a wide spectrum of topics. There have been a lot of interesting developments. So instead of trying to do the impossible of covering everything, my plan is just to focus on a few topics, 7 or 8. And in each case, I plan to discuss a recent paper or 2. So all these papers are going to be part of some bigger project. So we'll see what the questions are in the field. Okay, but before going to the papers, I'd like to say a bit about future observations. There's a lot to look forward here. The one that I'll talk about is high-frequency gravitational waves. This is a field at its infancy, but potentially of great importance for our field. The universal nature of gravity implies that there are many sources for stochastic gravitational waves, cosmic strings, phase transitions, oscillons. Most of these are model dependent. But there's one that's guaranteed by the hot Big Bang model, and also, interestingly, UV sensitive. So how does this arise? Well, at temperatures below M Planck, where the hot Big Bang operates, gravitons are not in thermal equilibrium with the cosmic plasma, but they're constantly emitted due to fluctuations of the plasma stress tensor. So for an observer today, these emissions sum up to give what's been called the cosmic gravitational wave background. The theoretical computation for this background in the case of standard model and the BSM have been computed. The result is summarized in terms of this differential equation. On the left-hand side, we have the contribution to the gravitational wave energy density today per log frequency band during one e-folding of the universe. And on the right-hand side, a source term that depends on the plasma under consideration. Let me summarize the features of this spectrum based as they follow from this differential equation. Firstly, the peak. Well, for most gravitons, the frequency at the time of emission is the temperature of the plasma at the time of emission. And after emission, a graviton redshifts as 1 over AT, and the plasma's temperature is also doing the same. So they're tracking each other. And this is essentially true for all gravitons, irrespective of when they're emitted. So the peak frequency of the CGWB today should be same as the peak of the CMB, which is in the gigahertz band. Now let's look at the amplitude. Well, it turns out the amplitude is proportional to the maximum temperature of the plasma, the maximum temperature attained. And this is simply because there are more e-foldings in the past. And the appearance of Tmax means that this is UV sensitive and very interesting for high energy physics and quantum gravity. So what are the prospects that we observe this? Well, today's experiment operates far from the gigahertz band. At the same time, there have been many interesting developments in the high-frequency range in both theory and experiment, and they're summarized in this living review. To the extent that the first experiments have already been sanctioned, and so we should be turning on these experiments in a few years. The proposed sensitivity of these experiments is orders of magnitude what we need to observe the background that I talked about. They'll be looking for other phenomena, but we should be optimistic as this is the start, and the quantity we are dealing with essentially probes the earliest times in cosmology. Now I'd like to move on to the papers. First, I'd like to start with moduli stabilization, because this forms the basis for much of string phenomenology and string cosmology. What I'll look at as type 2b flux compactifications and hierarchies therein. Integer data such as flux quanta and racks of gauge group characterize string compactification. And it's always an interesting question to ask, what hierarchies can be generated from these integers? Hierarchies from exponentials are very well known, but we'll report on the possibility today of having these from polynomials. So first, the setting, it's 2b flux compactifications. We have free-form flux, F and H, obeying an imaginary self-dual condition. This gives the potential for the complex structure moduli and the dilaton. There is no potential for the Kähler moduli. There's a well-defined 4D effective field theory description by the Gukov-Waffa-Witten superpotential. The flux introduced has to satisfy a tadpole condition. The maximum flux contribution of the flux to the D3 charge is limited. So this is a very well-defined system, yet finding solutions of interest phenomenologically has been hard. And let's go through why. Firstly, the tadpole condition by itself does not cut out a compact subspace of the flux vector space. So we don't know where exactly our solutions are in this flux space just from this. And more practically, the Calabi-Yau periods are just known as expansions in patches. So in the present work, the following approach was taken, that we work locally in a region of the moduli space, even within a patch for the period expansion. This can sometimes be needed for the validity of the effective field theory. And we use variables motivated by special geometry of the underlying Calabi-Yau. With this, the ISD condition simply becomes a matrix relationship between the flux vector, and the ISD matrix is closely related to the gauge kinetic matrix of the n equals to 2 theory. And having done that, one can arrive at bounds on flux vectors in terms of local properties of the gauge kinetic matrix, local in the moduli space, and here are some sample bounds. So we're sharpening these bounds, we're trying to understand them better, but at present, they're strong enough for us to be able to isolate interesting solution by using existing numerical methods. So I'll just give an example. So consider the symmetric locus of the Calabi-Yau in P11169. It has effectively 2 moduli, will work in the large complex structure limit. Here, the prepotential is a polynomial, and implying the same for the superpotential. So then we find that for the following choice of the flux vectors, the expectation value of the Gukov-Waffa-Witten superpotential is of the order of 10 to the power of -5, a lowered scale of supersymmetry breaking, and potentially an interesting control parameter. So this is just an example. I think we can now start systematically finding flux vectors so that we get properties that we want. So in some sense, it's looking at the inverse problem. Now, a few general comments on the work. The present approach provides explicit flux quantum numbers for the solutions of interest, so it should open up the avenue for more top-down studies. We have explicit access to features such as mass hierarchies, voids in the moduli space. It should be considered complementary to the statistical approach to study these vacua. We're in broad agreement with these results, but with some interesting differences. Okay, now I'll switch gears, start talking about acceleration. Observations have established that today's universe is accelerating. At the same time, accelerating solutions in string theory have been a challenge. And this is due to certain no-goes, which say that classical compactifications of 10D supergravity have no accelerating FRW solutions. Luckily, there are many no-goes. If we have singularities in the metric or the War factor, time dependence in the internal metric, corrections to the two derivative actions, localized sources, they all provide loopholes to these no-goes. But right now, there's no general understanding of when a particular loophole can evade and we can get acceleration, or if any part of it survives in general, such as in the de Sitter Swampland conjectures. So therefore, it's very fruitful to make successive construction programs of models and see what we get. I will start with some de Sitter constructions, ongoing de Sitter constructions. The one that I'll discuss in detail is based on the Salam-Sezgin solution. A quick recap on the solution. It's a solution in 6D10 supergravity. The part of the Lagrangian relevant for the solution is this. Phi is the tensor multiplet scalar. It has a runaway potential, so there is no maximally symmetric solution in 6D. But Salam and Sezgin found a solution in 4D, a Minkowski solution, which was an S2 sphere compactification. Now later, ADS and DS solutions were also found when allowing for localized sources. And in some sense, de Sitter came out naturally, given the positive nature of the potential. So given this, there is a program to look at string compactifications to 6D10 and further compactify to try and get de Sitter. The compactifications considered so far involve M theory on elliptically fibred Calabi-Yaos, leading to n equals to 2 theories in 5D, and then uplifted to 6D. As we heard earlier on, this leads to a large number of 6D theories, and only the simplest one has been studied in detail for this purpose. And this essentially is a two-field analog of the Salam-Sezgin setting. In addition to phi, a hypermultiplet starts playing a non-trivial role. Now, this 6D theory has de Sitter solutions. The associated metrics are warped. They have cylindrical symmetry. But as expected from the no-goes, there are singularities, and they show up in the War factor. But the properties of the local objects associated with the singularities can be computed using their asymptotic behavior. They have positive tension, but no D3 or D7 charge. So the final step of interpreting these singularities in string theory is underway. Now I'll give an update on recent work in constructing KKLT vacua. I'll be very brief here because this was discussed in detail in the last strings meeting. So this is a systematic search for KKLT vacua in Calabi-Yaos from the Kreuzer-Skarke list with less than or 8 equal to complex structure moduli. Many general methods in computational mirror symmetry have been developed for the purpose. They'll have wide applicability. But a few comments that I'd like to make on this construction. The expectation value of W0 is small, but not very small. And also, some of the two-cycle volumes are small, and alpha prime corrections have been incorporated for the purpose. Now, let's straight go to their summary table for the top 5 candidate de Sitter vacua. As they point out, their biggest shortcoming is that GSM, which sets the size of the S3 at the bottom of the Klebanov-Strasser throat, is order 1 at best. So the question to keep an eye on is, how does this change as they increase the number of complex structure moduli? Because after all, 8 is really a very small number. Okay, so now just one slide on Bruno's talk. Well, I think the message to take there is that if we are not tied to low energy supersymmetry, there are other possibilities, and they might be attractive for many reasons. Okay, next, I'll move on to acceleration as motivated by the Swampland program and its implications. For this, first, a brief review on the Swampland story. The Swampland program aims to take lessons from string theory and arrive at consistency conditions on any low energy effective field theory compatible with quantum gravity. So we'll need the Swampland distance conjecture, which says that as one approaches the boundary of moduli space, there is an exponentially light tower of states. And this has been also generalized to the emergent string conjecture, which says that the tower must either be a KK tower or string tower when viewed in the right frame. Similar reasoning can be applied to other parameters in the theory. For instance, in ADS, the tower scale is supposed to scale as a power of the cosmological constant. Now, for our universe, in the de Sitter or quasi-de Sitter state that we live in, it has been argued that m must be of the order of lambda to the power of 1/4. Now, one would like to connect this to the usual effective field theory reasoning. What is being said is that lambda, if one writes, that's just inverting this relationship. If one writes lambda as lambda 0 plus m to the power of 4th, the tower is contributing order m to the power of 4th, but there are no contributions to the CC above the tower scale. Plugging in the observed value of the cosmological constant, one gets that m should be of the order of 10 to the power minus 2 electron volts. And since there is no evidence for strong gravity at such low scales, this must be a tower, KK tower. Now, with this, the standard model must be on a brane. And then constraints from cooling of neutron stars imply that there must be one large extra dimension, which has been called the dark dimension. Although I'll not discuss it, more recently an alternate viewpoint has been taken, which says that we should think of the light neutrinos as taking us to the boundary of moduli space. And this suggests that there are two large extra dimensions. Various aspects of the cosmology of dark dimensions have been discussed. I'll focus on the ones related to dark matter. The first is KK gravitons as dark matter. So here, KK gravitons, dark matter, is produced from the decay of standard model plasma, and its abundance is determined in terms of the maximum temperature of the standard model plasma and the radius r. Furthermore, this maximum temperature can be related to lambda via the lifetime of the modulus that reheats the standard model and the Trans-Planckian cosmic censorship conjecture. In all, one has an expression for the abundance in terms of the cosmological constant. The dark matter here is also dynamical due to decay between KK towers, and which leads to one can compute the mass of the dark matter. And overall, there's a unification of scales in terms of the cosmological constant. The other possibility, which has been explored in detail, is primordial black holes as dark matter. And here there are two important differences from the 4D case. Firstly, that 5D black holes live longer than 4D black holes. And also, since the size of the extra dimensions we're dealing with is of the wavelength of visible light, the microlensing constraints are significantly weakened. And this leads to an enhanced range for an all PBH interpretation of dark matter. The lower mass region is extended by 2 orders of magnitude. Now I'd like to talk about quintessence. The dark energy equation of state will be probed minutely by various upcoming experiments in the next decade. For dynamical dark energy, slowly rolling scalars are the natural candidates. We will focus on the case of an explicit example of a runaway potential from string theory, and then see how it has been confronted with precision cosmological data. So of course, with quintessence, in addition to the magnitude of the vacuum energy, there are a whole host of challenges. But first, we have to find the runaway solutions. And this itself is a challenge. It's because the candidate runaways are usually too steep in the asymptotics of field space. Given that situation, it was quite interesting when explicit runaway solutions in type 2A were found. These were flux compactifications on Calabi-Yau or Einstein manifolds. From the 4D point of view, they were consistent truncations to two field systems with an exponential potential. Some features of the solutions, there were FRW metrics with negative spatial curvature. There was time dependence in the internal metric and the fluxes. In the Einstein case, the internal manifold is negatively curved. And in the 4D picture, asymptotically, it's a single exponential with lambda greater than square root 2, the bound that I mentioned earlier. Now, further analysis of these solutions showed that string and curvature corrections are under control. And also, interestingly, there are no cosmological horizons in keeping with low energy arguments. So this was good motivation to make a dynamical phase space cosmological analysis for the k equals to -1 universes with an exponential potential instead of the cosmological constant and cosmological fluids for matter and radiation. Let me summarize the result. Firstly, there's a future fixed point with a double dot equals to 0, so where one is not accelerating. But all solutions approach this fixed point, and they're accelerating while doing so. And if we want an epoch of radiation domination, this requires that the exponent be less than square root 3. And one can try to make the order 0 picture work, and it does. Here is a sample background cosmology, where I've shown the fractional energy densities as a function of the e-foldings. Then, since it looked good, people decided to confront the model with precision cosmological data. I'll not get into the details here because I think we'll have a discussion on it in the panel. But there, unfortunately, the analysis puts the exponent in the exponential at less than 1, well away from where we wanted it in the theory range of greater than square root 2. So, of course, the other side would have been more interesting, but I think the model exhibits the kind of interesting interplay that we can get between our theoretical models and precision cosmology as that data gets better. But also, this solution is very interesting on its own right for theoretical explorations. Now, I'd like to move on to alternate histories of the universe, and in particular, cosmic strings, a new mechanism to get cosmic strings. So the history of the universe before the Big Bang nucleosynthesis is almost unconstrained, and string theory provides various well-motivated possibilities for this era: moduli domination, kination, cosmological stasis. And each of these has a rich phenomenology and could well have left its imprint on today's universe. We will focus on kination. So what is kination? Well, kination is an epoch of the universe where the energy density is dominated by the kinetic energy of a scalar field. The cosmology can be solved in this limit, and all I want you to remember is that Hubble here goes as 1/3T. So now the same dynamical analysis that I talked a few slides back, even for a k equals to 0 universe, gives the following result. It gives kination epoch as the global past repeller. So if we go far back in the past, kination is supposed to be generic. This, of course, gives good motivation for us to study its implications in detail. A consequence of kination is that kinating moduli can lead to rapid variation of couplings. In the 4D theory, our focus will be on the variation of the string tension as caused due to evolution of the volume modulus. To give a concrete example, in the large volume scenario, the canonically normalized volume modulus has an exponential potential, It can kinate in the early universe, leading to mu dot over mu equals to minus 1 over t. Now, let's consider the dynamics of a single cosmic closed string in the setting. One can go to the gauge. The usual gauge for FRW cosmology is gauge fix. And in the equation of motion, the quantity epsilon, which depends on the worldsheet, naturally appears in the equations of motion. And this quantity can be directly related to the physical size of the strings. So let's first step back and recall what epsilon did in the constant mu case, so no varying tensions. With constant mu case, epsilon dot over epsilon is 0, that it is time independent for subhorizon small strings, and that's essentially telling us that strings remain of fixed physical size, just as in Minkowski, and they're actually shrinking, therefore, in co-moving coordinates. But now, on to the varying tension case. The equation that determines epsilon is the following. Let's focus on the second term first, and we can plug in our expressions for Hubble, mu dot and mu, and we see that the second term is positive. And this implies that epsilon dot over epsilon is greater than Hubble, that is, strings actually start growing in co-moving coordinates. So this, of course, leads to a novel mechanism to get cosmic strings network independent from the Keppel mechanism. And what that is, that in a kinetic universe, we can have a small number of closed strings. They would grow, find each other, percolate, and form networks. So detailed studies in these lines have started. Okay, now I'll turn to inflation. So various cosmological observations of the fluctuations of the CMB all provide support for inflation. But also, for us, we should remember that inflationary paradigm is really tied to quantum gravity. So my goal here is to give a recent update on Brane inflation. But in this case, I'll actually take the historical route, because the model is reasonably well developed, and it explicitly shows the nice relationship between inflationary model building and the importance of working in a UV complete setting. As the name indicates, Brane inflation is inflation driven by Brane dynamics. Our focus will be on space filling, D3 and anti-D3 branes, point-like in the compact directions. R here is the interbrane separation, which will serve as the inflaton. And C0 and D0 are constants related to the D3 brane extension. This is a slow roll model. Of course, when one thinks of general Brane dynamics, one can have a lot more interesting possibilities, but we'll focus ourselves on the slow roll case. So when one computes the slow roll parameter eta, one observes the following expression. Now, in an isotropic compactification, the maximum separation of the branes is bounded, implying we can't have slow roll. But we should remember that the real obstacle is this numerical factor, and that's just a consequence of the D3 brane tension. One way around is gravitational redshifting. That's to consider Brane inflation in a highly warped region, say in the bottom of a Klebanov-Strassler throat. And here, one sees that effectively the brane's tensions are redshifted, and indeed, one can get a small value of eta. But the analysis revealed another important aspect, that is the potential that we are dealing with also depends on the volume via the D3 brane tensions. And to get controlled single field inflation, we need that all other directions in field space are heavy. So what we should have really done is looked at a total potential for R and V, integrate out the heavy direction, and compute eta for the light one. So thinking of the general form of that potential, in these compactification, a generic contribution to the total potential arises from non-perturbative effects associated with the universal Kähler modulus. And this quantity is constrained by holomorphy and the structure of the two-field moduli space. And these constraints leave their signature on eta, essentially, leading to a universal 2 by 3, implying generically no slow roll. Of course, there are non-universal contributions. One can try to tune the non-universal ones to cancel the 2 by 3 and achieve inflation. This was pursued in some detail. But what this does is it changes the shape of the potential to inflection point 1, and this is not currently favored by the data. Therefore, there has been a revisit of Brane inflation in warped throats, but now with a concrete realization of the idea to use perturbative corrections to the Kähler potential to stabilize the volume. So we're in a regime where the dangerous non-perturbative effects are not relevant. And in this case, the high-scale potential essentially is a sum of two terms. One can integrate out the volume, and inflation can be realized using a concave potential. Well, that was one model. I'm putting up a summary chart of the model. There has been a similar story in each one. Maybe we'll discuss some of them further and how they're facing data in the discussion session. Finally, I'd like to return to the subject of high-frequency gravitational waves, but now from a more theoretical point of view. Recall that we saw that the amplitude of the background in the case of the standard model, or BSM, was proportional to T max. So it can serve as a probe of the maximum temperature, but it can potentially probe a lot more of what was there in the early times. I'll just discuss two things that have been explored so far, which can be of interest to people here. Firstly is gravitons produced from a strongly coupled plasma. That is, the early universe could well have been in a strongly coupled plasma sector. And here, a toy n equals to 4 super Yang-Mills has been taken as the universe. And using holographic methods, the gravitational wave production has been computed. And there one can compare the weak and strong tooth coupling results. And it was found that there's a roughly 5-factor change in the amplitude, but no major changes in the spectral shape. The other thing that has been explored is gravitational waves from high-temperature strings. That is, we have a situation where the standard model is realized by open string degrees of freedom. The early universe was hot enough so that massive open strings on the Brane were in thermal equilibrium. As the universe cooled, the massive strings primarily decayed to the standard model degrees of freedom, producing the standard model plasma. But a fraction of the decays were to gravitons. This is a Planck suppressed process, so it's subdominant. But this is going to give us a gravitational wave background. And what does it give us today? So I'll skip the details because Gonzalo has a poster on this. But let's again look at the features. Firstly, the frequency is close to the CMB peak. Now, the amplitude is actually proportional to the string scale, the universality, the UV sensitivity I was talking about. But it's large. It's large in the sense that it is orders of magnitude in comparison to what the standard model would give if it were at the same temperature. One can do a comparative plot at this toy level, at the level of this toy model. And there are also interesting shape differences. But I think the message from this model is that high-frequency gravitational waves can be a direct probe of the string scale. And therefore, we should try to make this connection strong. And there can be work at the level of model building, but also there should be work to do at the level of the general theory, just as in case of the CMB. Okay, so I was planning to go through each of these sections that I talked about, but I'll skip that in view of time and just have my general remarks on the conclusion that we've discussed only a collection of topics in string cosmology, focusing on a very few papers. But I hope that I've convinced you that there's a very rich connection between strings and cosmology. So, well, we've gone through various cosmological epochs. And in each case, strings played a role. I mean, from the earliest times to even the present epoch, strings did not have to play a role, but we saw that UV structure of string theory was important. And each epoch also raised questions related to our understanding of string theory, both at the technical and conceptual levels. And in the coming years, we can expect a lot of observational inputs where templates will be expected from us. So we should try and make the best of this opportunity. Thank you.
We have time for questions. Sandeep? Sandeep Trivedi? Go.
Anshuman, I wanted to ask you about the quintessence models. Since you were trying to, or people have been trying to connect them to experiment, I was curious what the scale of supersymmetry breaking is in those models, because the challenge is to keep it at least at a TeV and then, you know, the cosmological constant and the mass to be as small as the Hubble scale.
Yeah. So, I mean, as I said, that question has not been addressed in this model. In fact, there's no standard model sector. So if you look within the model itself, of course, because there's nothing else, I mean, it's in some sense stable. You can check for loop corrections. But yes, I mean, I think people have just gone on and tried. I mean, it was on the list of things. But I think that, I mean, at some level, finding these solutions was also hard. So people probably just took the step of comparing.
Thank you.
Yeah, so I have a comment about the dark dimension scenario. So it seems to me that it's essential to the scenario, this assumption that the cosmological constant is set by the mass of the KK modes in the dark dimension. But there are many contributions to the cosmological constant which are much bigger than that one. And so I understand the scenario doesn't want to try to solve the cosmological constant problem, but if there's a solution to the cosmological constant problem, why shouldn't it cancel that contribution as well? Why is that one special compared to all the other contributions that are much bigger? So without a scenario, an answer to that question, I don't see how we can say that that scenario is likely or plausible or something in the context of string theory.
Yeah, well, I agree, and I think maybe Miguel can, comment on this.
Yeah, so, I mean, so it's true that dark dimension, for instance, what you're, in our universe, that question is about, for instance, why electron loops, they should contribute to the dark energy. The dark energy scale is much smaller. So that's the cosmological hierarchy problem. Dark dimension doesn't solve that. I would say that no, and I think it's a super important problem, and I would say that no, the Sitter scenario or dark energy scenario string theory is addressing that. So for instance, if you look at the candidate, the Sitter vacua for the KKLT that we were hearing about, there was this paper by Ralph Blumenhagen showing that they actually satisfy dark dimension. There's the KK modes on the warp throat. They go like the cosmological constant to the 1/4. Casimir energy vacua, we were hearing about those yesterday by Bruno. Just by construction, the Casimir energy is one of the main ingredients to the vacuum energy. So but you're right that, we have a big problem there. I wouldn't say it's about dark dimension. I would say it's about, Fernando was asking about this yesterday at Bruno's talk, right? He was asking, where do you put the standard model? And Bruno was saying one step at a time. And it's true that we are not there yet at a step where we are addressing this problem, which I agree with you is like just super important, right? It's a big elephant in the room. But I don't think it's about dark dimension. I think it's about every model of dark energy that we have in string theory. We are at that earlier stage of development, unfortunately. We're just forgetting about that. We're forgetting about the standard model, just trying to get any dark energy model that works.
But this scenario has to treat KK modes differently from electrons, right?
I don't think it's different from any scenario. At the moment that you put electrons in any scenario, things go out of the window, is what I'm saying, okay? So yeah, somehow you need to find a way to deal with that. Yeah. But that's not specific to dark dimension.
So I have a comment about this. So this situation that Daniel's mentioning appears also in the regular string perturbation theory. Namely, when you talk about non-supersymmetric string backgrounds, like O16 cross O16 string, you find that the string tower cuts off the contribution of higher excited states in the tower. So there also the question exists, why didn't, let's say, the string level 10 to the 10 contribute to the cosmological constant? And the way that happens technically in string perturbation theory is the modular invariance shuts it off. The SL2Z symmetry gets the contribution back to just the string level of the excitation. So in that case, the tower sets the scale. And your question would have existed, and the magic there, which explains it, is the modular invariance of string theory. So what you're asking is what is the general magic of SL2Z, or the analog of modular invariance is the full setup, which of course we don't have a general explanation. But I think that those examples and many others that was mentioned already suggest that there is always such a mechanism, even though we don't have a deep explanation of why or how.
Okay, more questions? If not, let's thank the speaker. And now we have Paolo Creminelli with short presentation.
Okay, can you hear me? Good, so first of all, let me thank Hamed and the other organizers for setting this beautiful meeting and inviting me. So I'm going to talk about something complementary to what was discussed before, and which may be of interest to this audience, which is the issue of the beginning of inflation. And so I'm going to assume that one of the model of inflation is there. So I fix a given potential. And my question is, once you are given this potential, whether inflation starts. So in other words, what are the initial conditions that we should put on this problem? So inflation was introduced to solve the fine-tuning problems in hot Big Bang cosmology, but now the question is, what is the initial state for inflation? And so the question is a bit ill-defined, and indeed I want to present two alternative approaches, maybe there are others, to address this problem. So of course in each case the question is a bit different. So one approach is, I call it a cosmologist approach or attractor approach. So in this approach, one wants to show that inflation is an attractor. So of course, we know that locally, slower inflation is an attractor, so small perturbations are stable. But here I want to show that starting from generic classical initial conditions, inflation starts and solves, give rise to a homogeneous isotropic universe. So in order to address these, in order to prove these and to show that inflation is generic, one can take different approaches. So one is numerical. And so here is the list of references, and some of the authors are in the audience. And in this approach, one uses the fact that nowadays we can simulate numerical GR. So one takes a box, and instead of starting with something which is similar to an FRW cosmology, one starts from a very, very inhomogeneous universe in which the inflaton is not homogeneous, and maybe there is matter, radiation, whatever you like. Okay? And then you let your code run. And what you find, as you expect, is that you form a lot of black holes because overdense region will collapse, so you form a lot of black holes. But inflation is quite generic, so somewhere in the box the inflation starts and eventually becomes very big and dominates the box. So these studies in particular addressed what is called the initial patch problem. So in order for inflation to start, you don't need a homogeneous patch. So usually one can say that, okay, inflation will start if I have a patch, a Hubble-sized patch, which is homogeneous. But this, of course, is a very, very stringent request, especially if Hubble is small. But it turns out that you don't need this. So you are going to start inflation generically, even starting from very, very inhomogeneous initial conditions. So this is the numerical approach. One can also try to make progress analytically. And let me show some result. So in this case, one can simplify the problem and first of all try to prove that given a positive cosmological constant, so we forget about the inflaton, we just put a positive cosmological constant, and we want to show that starting again from very generic initial conditions, you converge to de Sitter. So in some sense, it's some sort of de Sitter no-hair theorem in which the evolution brings you to a de Sitter phase. So there is an old result by Wald showing that for a homogeneous anisotropic universe, you go to a de Sitter phase, unless it's a Bianchi-9 model. In this case, there are other assumptions. There is a very interesting theorem that I call it no recollapse theorem, which states the following. So one worry that you might have is in this situation is that you start forming black holes, and there is the danger that these black holes percolate and just the universe just recollapse before inflation starts. So it turns out that you can prove under general conditions that this cannot happen. And the reason basically is that in a universe which globally recollapse, there is a surface of maximal tree surface. So there is a maximal slice of maximal volume. And you can prove that this cannot happen under some topological restriction on the manifold that you are describing. So for instance, if your simulation is a tree torus, on a tree torus there are constraints on the Ricci scalar that you can put, and this allows you to prove that you cannot recollapse. So what happens is that you form a lot of black holes, but somewhere inflation indeed must start. Actually, this theorem does not prove that you converge to de Sitter. So some progress has been done to try to prove that not only you don't recollapse, but you, as you expect, you converge to a de Sitter phase. So people were able to prove it in 2+1, which is a much simpler case, and also in 3+1, but making some assumption about initial conditions. So in other words, it's a generalization of this theorem. Now the universe is not completely homogeneous, but it has homogeneity in two directions. So it's not a very generic case, but it's still more general than Wald case. And the tool here to study this problem is the so-called mean curvature flow. So I was saying, so this is one approach to try to prove that inflation is an attractor. So no matter where you start, you end up in inflation. There is another approach, which is more fundamental, which is, okay, I don't want to just scan over initial conditions. I just want to know what is the initial condition of the universe. And a very motivated possible wave function for the universe is the so-called no-boundary wave function. So in this case, one writes the wave function as a function of the metric and the inflaton perturbations at late times. And this wave function is calculated using the action for this geometry. And the geometry is deformed at early times in order to have no boundary. So it's a complex geometry with no boundary. So notice that this prescription is exactly, so this prescription gives the correct result if I'm interested in the small perturbations that we observe in the CMB. So if I use this procedure for the CMB, we get what we observe experimentally. So it smells the correct procedure. However, if you proceed, it turns out that what you get is the wave function, which has this form. And you see that this phi star is the value of the inflaton when the geometry basically becomes Lorentzian. So this means that the sphere, the radius of the sphere, when the geometry starts, in some sense, is pushed by this wave function to be very small. So in other words, this prescription prescribes a universe which is very small, and the inflation is very short. And of course, this is in tension with observations. Okay? So what's wrong with this? I don't know. Maybe eternal inflation can change the picture. Maybe we are just using the wrong prescription for the wave function of the universe. And this is a question which may be of interest. So thank you very much.
We'll take questions after all three short presentations. Ed?
Good morning. I've not met you, Acme, but hello. And thank you so much. I mean, this is amazing. And it's a pleasure to be here. So I'm going to tell you a little bit more about some of the recent things that I've been thinking about, but also to try and put in perspective the table that Anshuman gave you. So let me think if by just reminding some of you, or telling some of you, perhaps, what some of these quantities n and r mean. So inflation allows us to predict the form of the fluctuations for a given model. It's model dependent. And in particular, during slow roll inflation, where the potential is flat enough and dominates the energy density. So that means in that situation, we have the kinetic energy being much smaller than the potential energy, and the second derivative of the acceleration of the scalar field being much smaller than v prime. It allows us to then introduce these parameters epsilon and eta, which are our slow roll parameters. And one of the nice things about inflation is that you can quantify things in terms of these small roll parameters. In particular, the power spectrum for the scalar and the tensor fluctuations that we measure on large scales are given in terms of these parameters. So the power spectrum in the scalar sector has this power of ns minus 1, which is when ns equals 1, that's known as the scale invariant distribution. And ns minus 1 is given in terms of these epsilon and etas. And the power spectrum in the tensor modes is given goes as nt, where that's the scale associated with the tensor perturbations, and that is proportional to epsilon. And the R, which Anshuman talked about, is the ratio of the amplitudes of the tensor modes to the scalar modes. And what he was showing you was N, or NS, and R. Remarkably, we've measured AS. We've measured the amplitude of the scalar modes, and we've measured the spectral tilt in the scalar sector. We have not seen any evidence of tensor perturbations. So we have a bound on the amplitude of the tensor modes. So they're now no more than 3 or 4% of the total contribution to the power spectrum. So what I find remarkable is that when epsilon and eta were introduced as slow roll parameters, they were thought to be the same order. So we would expand things to order epsilon, or an order eta, or epsilon squared, an order eta squared. We'd always pair them together. Data's telling us now that's not such a good idea. The prediction is a nearly scale invariant spectrum, but epsilon is of order 0.002, and eta must be bigger than 0.01. So actually there's a if you like, a new hierarchy emerging. And that has an implication on the sort of forms of potential that are allowed. And the way we constrain these from the CMB is through these type of plots. So this is why Anshuman was giving you N versus R. And this is the data down here from the Planck and BICEP and Keck collaboration. So R now is bounded to be below about 0.036, okay? And these are all different models that were in the literature. And you can see, there is power here in the CMB to constrain models of inflation, to constrain the early universe. It is there. And so basically power law models, these are all single field models, are now in a bit of trouble. And so we're left with groups of models which have to live down here, okay? So what's the future? Well, the future are things like LightBird or the Simons Observatory, which are still going to be trying to probe for evidence of polarization in the CMB. So trying to probe R lower and lower. So this is the LightBird prediction. It's a Japanese-funded satellite that will be sent up towards the end into the 2030s, end of the 2020s, 2030s. And here are some ideas of what it says its constraining power will be. And so you can see it's gone down by a factor of 10, okay, in R. And so these include models like this is a model of our chair, a string-motivated model, the Poincaré disks, measuring, and you can see where this is where the power law models are living, way up here. Okay. So one of the things that Anshuman mentioned was this, I think he called it unusual cosmology, so not mainstream. So after inflation, what happens? The typical picture has always, in my head, has been inflation ends and the universe reheats. Just get on with it. You form, the hot Big Bang emerges. But actually in some models, especially string-motivated models which have moduli fields evolving, there's actually a long period of time, relatively speaking, between the end of inflation and when we would reheat the universe, when the moduli would become stable and the universe would reheat. And in this long period of time, which is generally the potentials of these moduli fields generally are exponential in form, then we can have these different periods of evolution. We can have periods where the kination period, where it's the kinetic energy of the scalar field that is dominating. And we can have periods of tracking, where there's a balance between the energy density stored in the scalar field and the energy density stored in any matter or radiation. And that final tracking regime is really useful because it allows the scalar field to slow down and then be trapped in what is usually a very small minimum. And that's the way of avoiding the overshoot problem. And one of the nice things is that this period can then, in principle, give to some new stringy features which will emerge. They will always involve large field displacements. And in one sense, this, I think, is a reason why thinking about this from a string theory perspective is quite important, because you've got an underlying theory which has got some UV control in it. And so you can think about these large field displacement knowing that you've got control over them. And there's also no necessary relationship between the inflaton field and the field responsible for the reheating. This is just, for example, the volume modulus that's evolving in this case. And so we have these long kination and moduli-dominated periods during this, leading to reheating at the end. And so what can emerge? What might be of interest to people? Well, these are moduli fields. This is string theory, right? So these are your coupling constants of nature. They're the ones that we think of as being constant but small generally. They're evolving. They're evolving in time over this small period of evolution as the universe is heading out to the edge of the moduli space. So you've also got perturbations growing in these fields, developing and growing. So as the fields are evolving, they're perturbing, they're emitting gravitational waves. You can easily enter regions where you start with relatively little radiation, enter radiation eras, have tracking regimes, and then get stabilized. So you've got all sorts of, I think, exciting Big Bang, pre-Big Bang Big Bang nucleosynthesis physics going on here that has yet to be explored. Now, whether or not it will survive reheating, I don't know. But one of the things that we will see are gravitational waves, right? They're being produced. And gravitational waves don't seem to care about very much. Once they're out there, they'll just propagate. And so if you can get distinctive signatures emerging in this period, they in principle will propagate through. And you will see them today, with a bit of luck. In particular, one of the things that I think is potentially quite interesting is that, and then Anshuman touched on it, so I won't discuss it any further, is the fact you can create cosmic strings, or cosmic superstrings in this situation, but they've got time-dependent tensions. So there's a different dynamics going on. The usual evolution of cosmic strings are when they've formed from a phase transition, the field is stuck in its minimum of its potential with a fixed energy density, fixed string tension, sorry. Here they're dynamic for a while, before they eventually become fixed. What's the new physics that might emerge there? So strings can survive, if strings can survive inflation, if you can form strings at the end of inflation, and we heard from Anshuman ways that this can be done, then they could be of interest. And if you're lucky, if nature has been kind to us and given us, say, Calabi-Yau spaces with deep throats in them, then you can produce strings which are long, can stretch across the universe, and have very small tensions. Yet they're cosmic superstrings. They're coming from string theory. And I was lucky enough to work with two great people, Rob, who's here, and I don't think there's many disciplines which has suffered the loss of someone quite as much as string theory has suffered the loss of Joe Polchinski. A quite remarkable person to work with, so I was very lucky to work with him. And these things can form in principle, and then they start evolving. But they form not just one type of string. You can form fundamental strings, you can form D strings, you can form pairs of FD strings, generically called PQ strings. They have some wonderful properties. When they intercommute, they don't always intercommute with a probability of 1. They can intercommute with a probability less than 1. If two different strings meet each other, they can't simply intercommute because they've got charges on them. They have to form bridges. So you can form new sort of networks of strings which have these bridges there, as well as the ordinary strings. And you can work out what you think the evolution equations are, and I'll finish with this. So these are the evolution equations for a network of such strings. They have the property that they reach scaling solutions where the energy density in the strings becomes a fixed fraction of the background energy density, so they're not dominating and they're not disappearing on you. And then you can ask the question, how do they contribute to the gravitational wave spectrum? And if you're lucky, these strings are emitting gravitational waves. You can work out the energy density as a function of the frequency. And you see, if you look in this regime here, 10 to the minus 9 hertz, they've got some interesting features. They've got some interesting features there. 10 to the minus 9 hertz is where nanograv is. Nanograv hasn't yet claimed a detection, right? It's evidence for, but I've made it look as if ours is the first paper to do this. We're not. In fact, the nanograv people did this. So cosmic superstrings are there in their minds. There have been about 3 papers. We're hanging on the coattails, but we're doing hopefully the proper evolution equations for this network. But people are thinking about cosmic superstrings, and I find it quite amusing that the standard paradigm for to explain these features, here, by the way, is the nanograv data. So one thing just to bear in mind is this don't worry about the frequency here. We've screwed up on this, should be 10 to the minus 9s. But this data point here is actually driving a lot of the data, a lot of the results, and I don't quite know why. But the standard paradigm that people say it is most likely to be, I find amusing, it's colliding supermassive black holes. That's your standard picture. But for a number of authors, this is a better fit. The cosmic superstrings is currently a better fit. So be optimistic. Okay, thank you.
We'll have questions for all speakers after Naomi's talk.
Okay, while we're waiting for the slides, I'd just like to echo everyone by thanking the organizers for putting together this beautiful conference. And so if you haven't noticed, we're taking you through a timeline of cosmology. So Paolo started with initial conditions, then we talked about inflation, and I'd like to take us through the rest of that journey after that time and even up to today by telling you about axions. Okay, so I want to start by telling you why I think string theorists should care about axions. And the first and most important reason is that there are many ongoing experiments searching for axions. And this is potentially one of the most exciting prospects for new physics in our lifetimes. Second of all, axions are ubiquitous in string theory. It's very hard to make theories without axions in one form or another. And finally, the physical characteristics of axions are extremely sensitive to UV physics. And so one really needs to have a theory of quantum gravity in mind in order to say anything about the physical properties of these axions. And so what I want to impress on you is that axion experiments can teach us something about where we live in the string theory landscape. Okay, so I'm going to tell you about the axion experiments and then about axions in string theory. Broadly speaking, there are a few different categories of axion experiments. The first category has to do with the couplings of axions to photons, so this is what they probe. These are astrophysical tests, probes of dark matter, and birefringence in the cosmic microwave background. There are also experiments that similarly probe axion couplings to fermions in similar ways. And I want to stress also that there are even some laboratory experiments and that we'll be able to probe the neutron EDM to greater precision in the coming years. And finally, there's sort of a grab bag of things that don't couple to fermions or photons, which are things like these experiments. On the other hand, there's a plethora of different types of axions that we can get in string theory. So you can pick your favorite string theory to begin with as a setting to look in. Then you can have compactifications or solutions of these string theories in all different sorts of ways: geometric, non-geometric, Calabi-Yau compactifications. And finally, within any of those solutions, you can have axions that come from closed strings and axions that come from open strings. And what I really want to impress on you is that each combination of observation or experiment and string theory setting for axions is a fruitful direction to look in. And that what we really hope to understand is whether there are any universal patterns in these settings, or whether there are any distinguishing observations or experiments that can be done to tell us where we live in this landscape of possibilities. Okay, so I want to tell you just about one such example now. So I'm going to pick a collection of these things. So I'll talk about dark matter probes in the setting of type 2b compactified on a Calabi-Yau, and I'm going to focus on these closed string axions which come from four-form gauge fields. Okay, so the example that I want to focus on is the QCD axion. If you like, this is my axion of choice. So this, I'm going to look at axions as dark matter. And I want to stress that in our lifetimes, there are enough experiments such that we will know whether the QCD axion composes all of the dark matter. So this is an important place to understand what we know in string theory. So we considered type 2b string theory compactified on a Calabi-Yau threefold in the geometric regime. And we focused on the case where the QCD axion descends from a C4 gauge field in this way. And the key question that we'd like to understand is if one of these experiments searching for QCD axion dark matter sees a signal, what would we learn about our place in this corner of the landscape? So what we did specifically is we constructed an ensemble of some 200,000 Calabi-Yau threefolds, and we considered a set of experiments which are all searching for the QCD axion as dark matter. So I can tell you more about what these experiments do later on, but these are all searching for QCD axion dark matter. And for each of these experiments, we computed the fraction of compactifications in our ensemble, which would produce a signal in that specific experiment. So just to show you the result here, on the x-axis, I have the number of axions in each geometry. In other words, the Hodge number H11 of the Calabi-Yau that I'm considering. And on the y-axis, I'm showing you the fraction of Calabi-Yaus that would produce a signal in each of these experiments. Okay? So what you can see is that each experiment is really indicative on a different range of n. So for example, this experiment DM radio is much more sensitive to the smaller values of H11 or n, whereas an experiment like MadMax probes a much broader and higher region of H11. So this is an example of how we can use observations to tell us something about axions in string compactifications. All right, so in view of time, I just want to leave you with some questions that I hope will lead to some fruitful discussion. First of all, I just presented to you, and this is the subject of a large ongoing program, statistical scans looking for properties of axions in the string landscape. But of course, we don't have a solution to the measure problem. So I'd like to ask you what we can hope to say about axion physics and string theory using these statistical scans. I'm happy to discuss this more. And also, I want to know your ideas about what the most pressing axion observables to compute in string theory are, given this landscape of upcoming axion experiments and observations. There's also an interesting interplay between the properties of axions in string theory and more cosmological considerations like moduli stabilization. And finally, I want to leave you with this question. Can axion physics or any axion observation tell us anything about computational control in our universe? What I mean by this is something like the following. If you consider the solution to the strong CP problem via an axion, we know that there's a quality problem. And in string theory, the solution to that quality problem really depends on being in a regime of computational control where things are nice and geometric and curvatures aren't too large. And what I hope is that there's some experiment or observation that can tell us whether we're in the regime where things are nice and controllable and computable, or whether there is more going on. So with that, I will thank you.
All the speakers, please go up. So I'll have one question to all speakers, and then everybody else is invited to ask questions. So the first question. I'd like to ask, maybe somebody want to talk about most important predictions of string cosmology and what kind of experiments will test them, say, in the next 20 years. Yeah.
Well, I think I touched on one of them. I think nanograph could be an important one. It'll be, and the nanograph is the North American set of experiments, but there are other experiments as well, also looking in this frequency range. I think this could be important for certainly testing the idea of cosmic superstrings. If you allow me a second one, I think both DESI and Euclid could be really important for us in trying to understand whether or not there's any dynamical evolution going on with the dark energy. And DESI's come out with its first set of results. There's been issues over whether or not it's really showing evidence for dynamical dark energy. It's a beautiful experiment, but Euclid as well will be able to do this. And I think we'll be hearing about that over the next few years. So I think these two sets of scales is really useful.
Yeah, well, I think Ed talked about this in his presentation. One thing that probably we'll know is about all the inflationary models that were on the list. There are some that will be probed by experiments like Lightbird, and
so this will be during next 2 decades.
yeah, and over the next 2 decades. And so that's something that we should all keep an eye on, and when we look at these models. And I think that maybe people can discuss this amongst the audience, that which models are interesting in that context.
Yes, thank you. Now we go to oh, you want to talk? Naomi?
Yeah, I mean, I mentioned this briefly, but you know, I think it's really exciting that in our lifetimes, that time scale, we will know whether the QCD axion is all of the dark matter or not. There are experiments planned and ongoing in every parameter region of the QCD axion, and so we will just know. And so if the QCD axion is there to be found as dark matter, we will find it.
But you are very young, so. So maybe I can add something that was not discussed. I think that in the next, maybe less than 20 years, in the next 10 years or so, we're going to learn something about non-Gaussianities from the large-scale structures. And in particular, I'm rather optimistic about the local non-Gaussianities, which are basically a smoking gun of a second scalar field during inflation. And I think there is a class of models in which basically the perturbations that we see in the sky are created by a second scalar field. And in all these models, we should see something soon, and this is something that is going to happen reasonably soon, in the next 5-10 years.
Thank you. Eva? Eva?
Thanks a lot for the talk and the discussion. I just wanted to add a couple of, in the spirit of Anshuman's talk being sort of forward-looking and timely, there are a couple of other kinds of observations that we can do related to theory using existing data. So one thing to stress is that it's not always about future data. If you have a new idea that hasn't yet been probed with existing data, that's sometimes an option. So the two I have in mind, one is very familiar, at least to Paolo, is the non-perturbative structure of the primordial scalar fluctuations. So we often focus on the power spectrum, the 2-point function, which, by the way, already can have a lot of structure inside of it, and then low point correlators, that, including the local non-Gaussian 3-point function that Paolo just alluded to. However, you know, it's a full probability distribution that we're looking at in the early universe, and non-perturbatively, there's a question of how, roughly speaking, how heavy the tails are, and we have sort of corners of the, let's say, field theory landscape where we've understood that the more information can be contained in higher point functions or equivalently on the tail of the distribution. And it's also the case that that can be a UV sensitive thing, sort of for the obvious reason that we're talking about large field excursions. So that's a live subject, and there's opportunities for new use of current data for that. Another one for fun is topology in the universe. It's been studied to some extent, but the kind of topology we're interested in for theoretical reasons these days, things with time-like boundaries that we'll hear about later today, have not really been optimally constrained in using even existing data. So that's another
Thank you.
one.
More questions? Lenny?
I'd like to ask you something I don't think anybody actually spoke about. How much room do you think there is for determining spatial curvature, the sign of it in particular?
Not much. Not much. The observations, I mean, of course you came up with this idea, right, that the universe may be open in string cosmology settings.
This is an experimental question, or
Yeah, sure.
Is there enough room that when
there's enough room for it to be either sign? Yeah, I mean the bound is on mod omega k.
How much better is the bound? That's the question.
Yeah. I don't know how much better the bound will get.
just a comment for string theorists, because usually cosmologists consider that our universe is kind of something originally maybe spherically symmetric, and then you have this wave function of the universe of this exponential type, etc. What's interesting is that if you consider toroidal universe, then there is no exponential suppression there. And that's an amazing fact. It's much easier to produce bagels than spheres.
So if I can say about the curvature of the universe, the recent DAISY data indeed help a bit in improving this. So I guess we are going to improve a factor of 2, a factor of 3 in the future, something like this.
Excuse me. I actually have a question about axions. So, as you said, a lot of string theories have a lot of axions. And in some ranges of axions, they would be troublesome because they would produce too much dark matter. How much of a constraint is that on model building?
Yeah, so maybe let me answer specifically in the corner of the landscape that I was talking about. So sort of the universal picture that we're finding through these scans is that as you go up in H11, the general picture of the spectrum of axions is that the masses are roughly log flat across the decades, but the axion decay constants decrease as a function of H11. And so maybe counterintuitively, as you go up in the number of axions, the decay constants come down, and so the total dark matter abundance actually decreases as a function of n. Moreover, because the axions spread all the decades in mass, you only have a few that can fall into the band where they can A, produce enough dark matter to be all of dark matter, and B, are not so heavy that they immediately decay. And so the answer is, at least in this corner of the landscape with many, many axions, it seems that dark matter is not much of a constraint.
Thank you. I actually maybe could ask another question. Do you have any comments on attempts to observe fuzzy dark matter?
So we actually just wrote a paper about this. I don't have much to say on the observational side, but on the string theory side, what I can say is that it seems that our best bet for finding models with fuzzy axion dark matter is at small h11, where the decay constants are large enough so that you can produce enough fuzzy dark matter. And you can do so without running up against the bounds that are currently there for fuzzy dark matter. One thing that you generically have to do, which I think is interesting, is you have to tune the cosmology a bit to be non-standard, because what typically happens is that if you arrange for one of your axions to be light enough, but have a large enough decay constant to constitute an order 1 fraction of the dark matter, what typically happens is that you have heavier axions with the same decay constant that overproduce dark matter. So you have to tune the temperature of reheating such that those heavier axions get inflated away and you don't overproduce.
I guess, sorry to keep asking questions, but is your corner of the landscape realistic enough that it makes sense to ask which of the many axions would be the QCD axion and what F axion would be for it?
By realistic enough, what do you have in mind?
To answer that question, your model has to include enough of the standard model so that you can say what is the QCD axion.
So an important thing that we always include in our models is that, so we imagine the standard model or QCD being modeled as a stack of D7 branes on 4 cycles. And what we always put into our models is that the volume of the 4 cycle that those D7 branes wrap is the right size to give the right gauge coupling of QCD at low energies.
Okay. And given all this, in your corner of the landscape, what is F axion for the QCD axion? Or is
it's a function of H11.
So what is the range that you get? Or maybe you showed us already.
So implicitly, I showed you with the graph, the plot of the different experiments as a function of n. But let me see if I can remember the numbers. At small h11, you're at about 10 to the 16 GeV, and then as you get up to hundreds, in H11, you can get down to 10 to the 8, 10 to the 9 GeV.
Thank you.
Any more questions to speakers or comments? Eva?
Sorry, I did just want to make, one more comment related to Dan Harlow's point earlier. The way, just technically, the way these de Sitter models work at minimum is what we call a 3-term stabilization for the volume. And what that means is that although the individual terms might be related to curvature scales, KK scales, there's always a small number in the problem that allows them to play off of each other, and the value of Hubble is parametrically smaller than is any of the individual terms in that 3-term stabilization structure. This is a thing we realized, very quickly after the discovery of the cosmological constant is a general thing about any such de Sitter model, and it's certainly true of the most recent one we heard of by Bruno yesterday evening. So I just wanted to clarify that. And just relatedly, we learn a lot of interesting things from string theory models, but we have to, keep in mind that there are, they can teach us about sort of phenomena that we may not have discovered in other ways theoretically, but that doesn't mean any very particular model is the one we should fixate on. It's a much more nuanced interaction that we have between string theory models and data.
So if there are no more questions, Fernanda.
Well, thank you all for the nice discussion. There are two things that were promised and we didn't hear that much, about the comparison of all the inflationary models and the comparison between quintessence and the cosmological constant. Can you say something about that?
So more about inflationary models, maybe Ed can show this slide.
So I think in the table you saw that at least in the range of models that were looked at, pretty much, I mean, a number of them are reaching the level now where, say, Lightbird will be able to rule out these basic models, but there's still quite a few that are surviving quite happily because the R is very small. In terms of evidence for dynamical dark energy versus cosmological constant, I think that's the big question, and that's why I think Euclid is going to be so important, as is DESI. Either way, I mean, well, I don't think we could in principle be in a position where we'll be able to say it's dynamical. I think I'm not convinced we'll be in a position where we'll be able to say it's a cosmological constant. I mean, you only need a small evolution to take you away from a cosmological constant. One thing which we haven't talked about at all, and it still seems quite amazing to me, is imagine we don't see any evidence for a cosmological constant, but we begin to see evidence that it's not -1. I think that would be really almost as big, because it wouldn't be a cosmological constant, it would be something else. And the evidence isn't there, of course, but yeah.
Thanks, Fernando. So with regard to your question, there are slides which one can look at, add slides, which have picture of possible models which are close to the data, and they will be tested. And this is the main problem with dark energy versus cosmological constant. We will hear from various experiments, but it is not very clear what precision we will have. But one have to keep in mind that the data will come. Thank you, everybody. Now, no more. Yeah. Questions, Sandeep?
No time.
No.